All right, we're about to dive into one of the biggest, most mind-bending ideas in, well, all of science, really. We're going to tackle the puzzle of what reality even is at its most basic level. So let's just kick things off with a pretty wild question, one that gets right to the heart of quantum mechanics. Does a particle actually have a location if nobody's there to see it? I know, it sounds more like philosophy than physics, right? But believe it or not, this is a real, honest-to-goodness scientific problem. And to even begin to unpack that question, we have to talk about the field it comes from, quantum mechanics. It's basically the rule book for how the universe works on the tiniest possible scales. And here's the thing you have to know. It is ridiculously successful. Its predictions are some of the most accurate in the entire history of science. But, and this is a huge but, for all its success in telling us how things are going to behave, this incredible theory leaves us with this deep, profound mystery about what's actually real. And this is the absolute key takeaway. The math? It works. Perfectly. I mean, it's the reason we have things like lasers and super powerful quantum computers. But the second you ask a physicist, okay, but what does it all mean? What's the universe actually like according to these equations? Suddenly, you've got a huge debate on your hands. And I mean a fierce one. Okay, so let's jump into the first, and for a very long time, the most popular answer to this whole puzzle. It's called the Copenhagen Interpretation.
This idea came about back in the 1920s from pioneers like Niels Bohr and Werner Heisenberg, and it makes a claim that is just completely radical. It basically says that things we take for granted, like the specific position or the speed of a particle, they just flat out don't exist in a definite way until we actually perform an experiment to measure them.
Now, the big idea here is something called the wave function. Before we look at a particle, quantum mechanics says we can only describe it with this mathematical thing. The best way to picture it is like a cloud of possibilities. The particle is in every single place it could possibly be, at every possible speed, all at the very same time. And this is the core of the Copenhagen view, broken down into two steps. First, you've got the particle just hanging out in this fuzzy superposition of all possibilities. Then, boom, the instant you measure it, that whole cloud of potential realities just collapses, and the particle is forced to pick one single definite spot.
You know, that sounds kind of neat and tidy, but this answer actually creates a giant plot hole in our understanding of reality. It's such a big deal, it even has its own name, the measurement problem.
This whole thing forces us to ask a question that sounds super simple, but the theory just doesn't answer it. What is a measurement exactly? I mean, does it count when a scientist glances at a screen? Or when a little detector goes click? And look, this isn't just some minor detail we're glossing over. This is a philosophical earthquake. It shakes the very foundation of the idea that there's a real world out there that just exists, whether we're paying attention to it or not.
And this slide just lays out this central conflict so perfectly. See, on one side, when we're not looking, that cloud of possibilities, the wave function, it just evolves smoothly. It follows a very precise, predictable rule called the Schrödinger equation. But on the other side, the instant a measurement happens, everything changes. There's this sudden, random, almost violent jump to just one state. So why are there two completely different sets of rules for reality?
This measurement problem was a huge headache for a lot of physicists. We're talking even Einstein himself, and it pushed them to come up with their own, often just as weird solutions to this whole quantum puzzle.
So let's take a quick look at the main rivals. You've got theories that say parallel universes are popping into existence with every measurement. You got others that claim there's some secret information we just aren't seeing. Each one tries to solve the mystery in a completely different and, frankly, mind-boggling way.
I love this slide because it really shows you the competing stories. Copenhagen says you, the observer, are special. You force reality to make a choice. Many World says, nope, no choice is made, but the cost is believing in an infinite number of parallel yous. And then hidden variables theories say there was never a choice to begin with. The outcome was always written in stone. We just didn't have the key. You can see how each fix comes with its own really bizarre baggage.
So after all that, with all these competing, strange ideas, where are we now? Have we actually figured this thing out?
And this, to me, is the most fascinating part. We've managed to run these incredible experiments that prove the weirdness of quantum mechanics is absolutely real. They've shown our old-school, common-sense view of the world is just wrong. But here's the kicker. These tests are designed so cleverly that they give the exact same results no matter which interpretation you believe in. They tell us that the universe is weird, but they can't tell us why it's weird.
And that's the number of interpretations that all physicists agree on. A big, fat zero. The debate that kicked off with Bohr and Einstein almost 100 years ago? Yeah, it's still going strong today.
And that is the grand irony here, isn't it? We have what is arguably the most successful, most precisely tested theory in the history of science, and yet the fundamental mystery at its very core, the question of what reality is still completely up for grabs.
Which brings us right back to where we started, to that deeply unsettling question. If the Copenhagen view has it right, then in a very real way, our observation doesn't just uncover reality, it helps create it. And that just leaves you wondering, what is our role in this vast, strange, and absolutely beautiful quantum universe?